the bird is moving with the velocity of 40 km per hour north, and the train is moving 40 km per hour east, then the velocity of the bird when somebody looked from the train is exactly look like the train is moving to the direction of the east and the bird is flying to the direction of the north with the velocity of 40 km per hour. So if somebody look at the velocity of the bird or the motion of the bird, it seems that since the train is moving this way and the bird is moving this ways, so this is velocity of the train and this is velocity of the bird. So when somebody looked at the bird from the train, it's look like the bird is moving in the direction of the north or west. So this is the velocity of the bird looked from the train, or relative velocity of the bird with respect to the train. So this velocity can be calculated as velocity of the bird with respect to train is the vector differences of the velocity of the bird and velocity of the train. So this is equals to directly 40 km per hour north minus 40 km per hour in the direction of the east. But these velocities are perpendicular to each other. We cannot directly subtract from each other. So to find the magnitude of velocity of the bird with respect to the train, the magnitude of velocity of bird with respect to train is calculated directly using the Pythagoras theorem, since the two velocities are orthogonal to each other. So this means 40 km per hour the whole square plus minus of 40 km per hour the whole square and the radical. So this is equals to twice of 40 km per hour the whole square and the radical, which directly gives us that 40 into radical 2 km per hour. So this is the magnitude of velocity of the bird with respect to the train. So since its direction is to the north of west, so the bird seems or looks when it's seen from the train moving to the direction of north of the west. That means the velocity of the bird with respect to train is 40 radical 2 km per hour to the direction of north of west. The correct answer is on alternative B. The stone is dropped from a high building and reached the ground in 2 seconds. So what is the height of the building from which the stone is dropped? So dropping is a free falling. So free falling is an example of uniformly accelerated motion. So always in dropping, if the object is dropped, we know that the initial velocity of that object is 0 and the time is given 2 seconds and g is known 10 meters per second square, and what is the height or the displacement traveled by the stone to reach the ground. So we have four quantity here: time, initial velocity, acceleration, and the displacement is. So we cannot see here the final velocity v. So among the equation of uniformly accelerated motion, we use the third equation. So since we have the 5 equations to solve the uniformly accelerated motion, the third equation says that s is always ut plus a half of g times t square in a free falling. So initial velocity is immediately 0 and this become a half of g t square, so which is equals to 1 over 2 10 meters per second square times 2 second square. So we can simplify here, this become 5, so 5 meters per second square for second square is, and second square cancelled by second square, and 5 times 4 is 20 meter. So the displacement or the height above which the stone is dropped is 20 meter. So the correct answer is on alternative B. football is kicked with a velocity of 25 meters per second at an angle of 37 from the horizontal. So if the ball is kicked from the ground at an angle of 37 from the ground is with a velocity of 25 meters per second, it follows a trajectory path, or it moves like a projectile. So what is the range of this projectile and the total time the ball spent in the air? So the flight time of the projectile is given by, we know that it is 2 times the initial velocity sine of theta divided by g. Directly, if we substitute the values, 2 times 25 meters per second times sine of 37 divided by 10 meters per second square. So we can see that this meter cancel, 1 second is cancelled, 1 over second, which become second only, and the sine of 37 is 0.6 immediately. So this become 2 by 2 is 1 and 10 by 2 is 5, and we have left with 5. 5 with 5 is 1 and 5 with 25 is 5. That is 5 into sine of 37 is 0.6. The second is only survive. This means 3 seconds. So the ball takes 3 seconds to reach the ground. And the range of this ball is given by is 2 times u square sine theta cos of theta divided by g. Directly, if you substitute the value, this is 2 times 25 meters per second, the whole square, sine of 37 degree times cos of 37 degree divided by 10 meters per second square. So just we can simplify this number still. This by 5, this by 2 is 5, and this by 2 is 1. And also we can simplify this with 5 and we get 125. This is 0.6 and this is 0.8. If we multiply the values, finally we can get 60 meters. So the time taken for the ball to reach the ground is t is equal to 3 seconds, and the range of the ball is 60 meters. So the answer which combine these two values is on alternative A. The rock is thrown upward with a velocity of 30 meters per second and reach some height and return back to the level at which it is thrown. So this is an example of a free falling, which is a uniformly accelerated motion. The initial velocity is given, acceleration due to gravity is known, and the time which the stone take into the air when it is returned or come back to the level it has thrown is, when the stone is come back to the level where it has thrown, the displacement traveled by the stone is immediately 0. So S is 0 when it's come back to the level when it has thrown. But don't be confused that the Hannah is standing on the hills or on the height of 100 meters. The stone goes up and returning back to the level where it has thrown. So this height is not included in the calculation. Don't be confused with this height. So initially, since the velocity and acceleration due to gravity are opposite, so I make one of them negative. That means the object is decelerating while it's moving up and accelerate, come back when it is moving down. So the motions of upward and downward are symmetry to each other. The third equation of the uniformly accelerated motion, S is equals to ut plus a half of a t square. So when the stone is returning back, S is immediately 0 and a is substituted by g, which is minus g. Then this is 0 is equals to ut minus a half of gt square. When this is transferred to this side, a half of gt square is equals to u times t, and t is cancelled from both sides, and t is equals to 2u over g. So the t is equals to 2 times 30 meter per second divided by 10 meter per second square. So this become meter is cancelled by meter, 1 second is cancelled by 1 meter, and only 1 over second is left, which become a second is 10, 0 cancelled by 0, 2 times 3 is equal to 6 seconds. So the time taken for the stone to return back to the level it has thrown is equal to 6 seconds. So the answer is on alternative A. Since the plane is flying toward Redawa, which is east of the Addis Ababa, with a velocity of 500 km per hour, and the wind is blowing to the south, to the direction of the south, with the velocity of 100 km per hour. Then the velocity of the plane when observed from somebody from the ground is the velocity of the plane and the velocity of the winds are perpendicular to each other. This means the velocity of the plane from the ground is the vector sum of velocity of the plane and the velocity of the wind. So this is the velocity of the plane from the ground observer. So that means the velocity of the plane from the ground is given by the vector sum of these two velocities. So since the two velocities are perpendicular to each other, I can use directly the Pythagoras theorem. So the velocity of the plane, the whole square, plus the velocity of the wind, the whole square, and the radical 100 km per hour square plus 100 km per hour, the whole square, and the radical 26 times 10 raised to 4 and the radical kilometer per hour, which is 510 kilometer per hour in the direction of the south of east. That means the plane is moving to this direction and the wind is moving to the south and the plane is moving to the east. So the vector sum of these two velocity is along direction of south of the east. So velocity of the plane from the ground is equal to 510 km per hour south of the east. So the correct answer is B. So the stone is thrown upward with some initial velocity and it passes through A, B, and at C it returns back to the ground, or it returns back. So C is the turning point. When the object is past the point A, it has a velocity V of A, which is equals to V. So the stone passes point A with the velocity V, and the velocity at point B of the object is V over 2. So velocity at B is reduced by half of the velocity at A. So that means the object is moving up, so it will decelerate. The velocity decrease with time, and at C the velocity become 0 and return back. So velocity at C is simply it is 0. So point A is h meter from the ground is, and point B is 3 meter above A, and point C is y meter above the B. So we don't know the heights or the climaxes of the object is from the ground. H is unknown. So the question says that what is the velocity V? Velocity V in value is how much, and calculate the heights of the object is from B up to C. Or just we are going to find also the y values of these objects. So to do this exactly, we can use the equations of uniformly accelerated motion, because we know G is acting downward always. So since the object is moving up, the velocity of the object is reducing, then we can use the G is acting downward, the object is decelerating while it's moving upward. So I can represent G is simply minus G, or I can substitute it by negative 10 meter per second squares. So exactly I can use equation number 5 from uniformly accelerated motion, which says that final velocity square is equals to the initial velocity square plus 2as. Velocity at a square is the initial velocity of the object square minus twice of g times h, where h is the distance from the ground up to point A. So this is the height is h at point A. And also the second equation is velocity at B is equals to the initial velocity of the object is minus twice of g into the height at B is the height from the ground up to point B is h plus 3 meters. So since we know that the velocity at A is directly v and velocity at B is v over 2, if I substitute into the equation, I have v square is equals to u square minus 2gh, and v over 2 the whole square is equals to u square minus 2gh plus 3 meter. This is the simultaneous equation. Then I can solve for v. This means first I rearrange this equation, which gives me v square is equals to u square minus 2gh, and so we can write v over 4, v square over 4 is equals to u square minus 2gh minus of 2g times the 3 meter, or this is 6 meter times g. So I can solve for v from these two equations. So in solving of this, I can eliminate u and the gh from these two equations by subtracting the second equation from the first one. So this gives me that v square minus v square over 4 is equals to u square minus 2gh minus u square plus 2gh plus 6 meter times g. So this means I subtract the second equation from the first one. That means first equation minus the second one. So this gives us that v square minus v square over 4 is immediately 3 over 4 v square, which is equals to u square minus u square is 0, minus 2gh plus 2gh is also cancel each other. We have left with 6 meter times g here. This is not mass, don't confuse it, is in meter, 6 meter, because we have 3 meter here, since point B is 3 meter above point A. So if we find for v from this equation, immediately we can see v square is equals to just 4 times 6 meter g divided by 3. Then we can simplify this, and 6 by 3 is 2. Then v is equals to under radical of 4 times 2 is 8 meter times g. So v is under radical of 8 meter times g. This is immediately gives us that under radical of 8 meter times g is 10 meter per second square. So I can substitute 10 meter per second square. So this gives me 80 under radical of 80 meter square per second square, which is immediately 8.94 meter per second. So velocity v is equal to 8.94 meter per second. So we have got the values of v. And the second equation says that find the height above B when the ball is turning back. That means the maximum height above B at which the ball will return back. That means we are going to find y. So since velocity at B is velocity at B is simply v over 2, it's known, and the velocity at C is 0, so VC is immediately 0 because C is the turning point. What is this height above B at which the stone will return back? So we can see that velocity at C square is equals to velocity at B square minus 2 gy, where y is the height between point B and point C. So velocity at C is immediately 0, as become 0. Then if I transfer and find for the velocity, find for y, 2gy is equals to velocity at B square, but the velocity at B is immediately is equals to v over 2. So if I substitute the value, so then 2gy is equals to vb square, and the velocity at B is v over 2. Then if I substitute and rearrange, 2gy is equal to v square over 4. That means 80 meters square per second square. That is velocity at B square, or v square is 80 meters square per second square, divided by 4 gives me 20 meters square per second square. So y is equals to 20 meters per second square divided by 2 times g. So if I substitute 20 meters square per second square divided by 2 times 10 meters per second square. So second square cancelled by second square, and 1 meter is cancelled by 1 meter. We can cancel 0 by 0, and 2 divided by 2 is 1. We have left with 1 meter. So the velocity v is directly, as we have calculated, it is 8.94 meter per second, and the height above B at which the stone will return back is 1 meter. So there is no answer among the given alternative. The position of the object is given in terms of time, the x and y position of the object is, where x is equals to 70 plus 40 square and y is equals to 5t, and where x and y's are in meter and t is in seconds. Then what is the acceleration of these objects if these are the initial position of the objects, or the position function of the object with respect to time? So you know that acceleration is always equal to the second derivative of the position function with respect to time. That is, if the position of the object is along the x, we derive x with respect to time twice, and if the position is along the y, we derive the y positions with respect to time twice. So this is from the calculus. Ax of t is equals to d by dt of d of x of t with respect to dt. So we derive it 2 times. So this is equals to d by dt of d by dt into 70 plus 4t square. So if we derive once, it becomes d by dt of derivative of 70 is 7 with respect to time, and the derivative of 40 square is 8t. And once again, if we derive it, we get this becomes 0 and this become 8. So this is the acceleration of the objects along the x-axis, that is 8 meter per second square. So since y of t is 5t, if we derive this twice, that means d by dt of y of t, or which is equals to 5t, we immediately get 0, because d by dt is once gives us 5, and the derivative of 5 with respect to time gives us 0. Therefore, the acceleration of the object is, which is ax I plus ay j. Simply, since dy is equal to ay is 0, we have left only with 8 meters per second square along the j. So since y of t, or position of the y, position of the object along the y is 5t, if we derive this second time immediately, it gives us derivative of 5t is 5, and if we derive for the second time immediately, it becomes 0. So the acceleration is only along the x-axis, which is acceleration of the object is given by only 8 meters per second. This ay is 0. That means just we can write the acceleration of the object is as the acceleration along x and the acceleration which is along y. This one is 0, only this is survive, which is 8 meters per second, as we have done before. So the correct answer is on alternative B. So an athlete is accelerated at a rate of 1.9 meters per second square from rest. So the athlete starts from rest and runs for 3000 meters, that is for 3 kilometers. Then initially its velocity is 0 since it is start from the rest, and for time t is equal to 2.2 seconds. So he accelerates for 2.2 seconds at a rate of 1.9 meters per second square. Then what is the athlete velocity at the end of the race? If this is the end line of the race, what will be the velocity of the athlete at the end of the race? So then we have to find the final velocity of the athlete at some point, or at the end of 2.2 seconds. So the velocity of the athlete at the end of 2.2 seconds is given by, from the uniformly accelerated motion equation. The first equation is final velocity is equals to initial velocity times acceleration times the time of the motion, or the time at which the velocity is increased or decreased. So this is immediately 0. So final velocity becomes a times time, which is immediately gives us a is 1.9 meters per second square times, and the t, or the time of motion, is 2.2 seconds. So 1 second cancelled by 1 second, and immediately we have the final velocity of the athlete is 4.18 meters per second. So velocity at this point is 4.18 meters per second. So this is the velocity of the athlete. So then, since the athlete is accelerated only for 2.2 seconds, the rest of the velocity is equal to this one, or the athlete will uniform motion up to the end of the race. So the velocity at the end of the race will be equal to the final velocity after 2.2 seconds if he continues with this velocity up to the end. So since the acceleration is only up to this point, so the final velocity at the end of the race will be equal to 4.18. So the correct answer is on alternative C. Okay, for any object is moving along the circle with a constant speed v, the object is moving along the circle of radius r with a constant speed v. So the object will accelerate always along the circle because the direction of the velocity of the object is changing. Even if the speed is constant, the direction of the motion of the object is continuously changing along the circle. So this means that according to the Newton's second laws of motion, if the velocity of the object is changing, there is a force which is acting on the object is to force it change its direction continuously. So this force is what we call centripetal force. It acts always toward the center of the circle. Fc is always acts toward the center of the circle. So the velocity of the object is changing in direction, not in magnitude. So since we know that the velocity is speed with some direction, so the speed is not changing, that means the magnitude of velocity is not changing, but the direction of the object is changing continuously along the circle. So then the force which makes the object is to change its direction is we call the centripetal force, which given by mass times the centripetal acceleration. Centripetal acceleration is also along the direction of the centripetal force according to the Newton's second laws of motion. So direction of centripetal force is toward the center of the circle. This means the direction of centripetal acceleration is also toward the center of the circle. So centripetal acceleration is given by the speed square divided by the radius of the circle along which the object is moving. So this means that mv square over r is the centripetal force. So according to the question, the force, centripetal force per mass is given by velocity square over r. So this is the force per unit mass of the object, which is v square over r. Force per unit mass means directly, we can say indirectly, it is a centripetal acceleration of the object. So the correct answer is on alternative D, which says the force per unit mass is velocity divided by the radius of the circle. So the car is initially moving with velocity 4 meters per second and it accelerates at a rate of 3.2 meters per second square for t is equal to 10 seconds. Then we can determine the final velocity of this car. So the final velocity of the car can be calculated from the first equation of motion, of uniformly accelerated motion, which is u plus a times t. So this is equals to 4 meters per second plus 3.2 meters per second square times t is 10 seconds. So we can cancel 1 second by 1 second, and 10 times 3.2 is 32 plus 4, which gives us 36 meters per second. Then finally the car is moving with this velocity and the brake is held. The brake is held with a car which is moving with velocity of 36 meters per second, and the car slows down and finally come to rest with final velocity 0 for traveled for 20 meters. Then in this case, what is the acceleration of this car while it is decelerating down? So since the car is accelerated from 4 meters per second and reached 36, and then after it has reached 36 meters per second, then the brake is held for 20 meters while it is decelerating. The car moves along the displacement of 20 meters. Then what was the acceleration of this car while it is slowing down? So from this, just we can use the fifth equation of motion, which says v square is equals to u square plus 2as. Then I can transfer v square minus u square is equals to 2as. Final velocity of the car is 0. I can take the initial velocity as a 36 because the car reached this velocity while it is accelerating in the first case. So this means that the acceleration of this car is minus its velocity is squared divided by twice of the s. This is minus 36 meters per second, the whole square divided by 2 times 20 meters. So while we multiply this number together, we get minus 32 0.4 meter per second square. So this is the final acceleration of the car while it is decelerating or after the brakes hold. So the correct answer is on alternative D, which says minus 32.4 meter per second square. So the ball rolls off the edge of the table, which is 4 meters above the ground, and the ball moves and landed at a point is 5 meters from the end of the table, or from the 5 meters horizontally away from the edge of the table. So then what is the time taken in the air for the ball to strike the ground? That means the flight time of the balls to reach the ground. So this is an example of horizontal projection. So in horizontal projection, the time taken for the ball to reach the ground is directly given by twice of the height divided by g and the radical. So this is immediately 2 times 4 meter. So the height of the table is 4 meter divided by 10 meter per second square. So meter is cancelled by 1 meter, and 10 by 2 is 5. So radical 4 can be taken away, it is 2, and times 1 over radical 5. So this is immediately is equals to 2 divided by radical 5 seconds. So the answer is on alternative D. So the river is moving with the velocity of 6 km per hour with respect to the ground, to the downstream, and the boat is moving with respect to the river at a velocity of 15 km per hour to the direction of the upstream. So the velocity of the boat with respect to the river and the velocity of the river with respect to the grounds are opposite to each other. Then what is the velocity of the boat with respect to the ground? And also the child is moving along the boat from back of the boat to the front with a velocity of child with respect to the boat 5 km per hour to the front side. Then what is the velocity of this boy with respect to the ground, or the velocity of the child with respect to the ground? So to calculate the velocity of the boat with respect to the ground, we have the relative velocity of the boat with respect to the river, which is velocity of boat with respect to ground minus velocity of the river with respect to the ground. So velocity of the river with respect to ground is given, velocity of the boat with respect to the river is also given. Since these two velocities are opposite, that means velocity of the boat with respect to ground and velocity of the river with respect to grounds are opposite to each other. So I make one of them negative. That means velocity of the boat with respect to ground minus velocity of the river with respect to the ground. So I make one of them negative since they are opposite. So velocity of the boat with respect to ground plus velocity of the river with respect to ground, which is the relative velocity of boat with respect to the river. So to get the velocity of the boat with respect to the ground, I transfer velocity of the river with respect to the ground to the other side. That means velocity of the boat with respect to ground is the relative velocity of the boat with respect to river minus velocity of the river with respect to the ground. This means that the velocity of the boat with respect to the river is 15 km per hour minus velocity of the river with respect to the ground is 6 km per hour. So this gives us immediately that velocity of the boat with respect to ground is 9 km per hour. So the boat is moving with a velocity of 5 km per hour with respect to the boat. That means the relative velocity of the child with respect to the boat is the velocity of the child with respect to ground minus velocity of the boat with respect to the ground. So this means that velocity of the boy or velocity of the child with respect to ground is directly equal to velocity of the child with respect to the boat. If I transfer this side, I get velocity of the boat with respect to the ground. So velocity of the child with respect to the boat is 5 km per hour plus velocity of the boat with respect to the ground is, we have calculated, it is 9 km per hour. Then the velocity of the child with respect to the ground is the sum of these two numbers, which is 14 km per hour. So the correct answer is on alternative D.